Bismillah ar-Rahman ar-Rahim. Alhamdulillah wa salatu salam ala Rasulillah. This chapter 4, we're going to study the transfer function. What do we need from this chapter? We need mainly to understand what is the meaning of a transfer function and how to derive the transfer function of any mechanical system. Also, we're going to talk briefly about the block diagram. What is a block diagram? How to draw the block diagram. Okay, we'll talk briefly about that. Okay, let's get started with the transfer function. Okay, what's the definition of a transfer function? Transfer function is the Laplace transform of the output over the Laplace transform of the input, assuming zero initial conditions. Okay, this is the definition of transfer function. Transfer function is the Laplace transform of the output over the Laplace transform of the input, assuming zero initial condition. Okay, you need to remember two things about the transfer function. Always, it's always in the Laplace domain. It's not in the time domain, it's in the Laplace domain. And also it's assumed always the initial conditions are zero, no initial conditions in the transfer function. Okay, all right, let's see the first example to understand the meaning or how to derive a transfer function of a mechanical system. Okay, what do we have here? We have single mass spring and damper system with external force. This is the degree of freedom, the single degree of freedom, x, and external force, f of t. Okay, find the transfer function. If the input, this is my input. Okay, so from now on, whenever we ask for the transfer function, the question should be clear about what's the input and what's the output of the system. So the input here is f of t. The external force is my input. And the output, x of, We always have this kind of error. It's a software error, always happening with everybody else doing PowerPoint. So let me go back to the pen. So this is my output. So x is my output and f of t is my input. Can you derive the transfer function? Find the transfer function. Again. This error always happening. Transfer function. The input in the Laplace domain, the input is capital F of s because it's going to be in the s domain. This is the time domain, and the output is x of s. Find the transfer function. How are we going to do this? Step number one, you need to derive the equation of motion. Of course, you know how to find the equation of motion, right? First, you need to derive or draw the free body diagram showing all the forces acting on this body. We did that in chapter 3, right? So now we're going to go and assume that you derive the equation of motion. And this is f of t, by the way. There is a typo. F of t. So this is my input. This is my output. How are you going to find the transfer function? First, take the Laplace transform, assuming zero initial conditions. So take the Laplace transform. All right. Take x of s out. And what is the Laplace transform of f of t? I'm assuming f of t is a function in the time domain, so in the s domain is going to be f of s. Okay, then find the transfer function. The transfer function, okay, just divide f by x, right? You want to get this, divide x by f, right? And take this to the other side. So the transfer function, x over f, will be 1 over ms squared cs plus k, and this is your transfer function. Okay, this is your transfer function. All right, as you can see, usually the transfer function, what you see, the denominator, the order of the denominator is higher than the order of the numerator. Okay, always, in fact. Okay. All right, look, this is my transfer function that I derived, okay? Can you find the order of the system? Yes, there is something we call an order of the system. How can you find the order of the system? By finding the power, the highest power of the denominator. So the highest power here is 2. so the order of the system will be second order. Okay, so this is a second order system. We care so much in dynamic systems and in control, we care so much about the order of the system. Why? Because first order systems always have the same behavior, similar behavior, okay, regardless of what kind of first order. Is it electrical, mechanical, or fluid, for example, okay? Second order system, they always tend to behave in a similar manner, okay? Regardless if it's a mechanical, fluid, biological, anything, any second order system, they will always behave the same. That's why we care so much about the order of the system when we derive the transfer function. Okay, so this is what we learned so far. Now we know how to derive the equation of motion. Okay, we derive the this typo, f of t. This is we call the equation of motion in the time domain. This is the equation of motion in the Laplace domain. This is the transfer function. Transfer function, by the way, of the system is a property of the system. Okay, it has nothing to do with the input and the output. It's independent of the input and the output. Okay. All right. So usually, if you know your transfer function, you can calculate the output. This is the output, which is the response. If you know your input, if the input you know it, and you know your transfer function, it's a matter of calculation. This is what's done in MATLAB. If you remember in the lab, when you use MATLAB to solve a system, you tell him, I want to find the step response. You need to define the transfer function. You remember that in the lab? Just tell him what's the transfer function and tell him what kind of input you have, and he will calculate it and he will give you the response. Okay, usually he plotted directly in MATLAB. Okay, also this is just for your information in control and in vibrations. If the transfer function is unknown, you are in the field, for example, and you have a mechanical system, for example, turbine or whatever mechanical system, and you don't know what's the transfer function of the system. So all you have to do, give the system an impulse in order to calculate the response or the output. So if this is a machine, for example, you give it a punch or a hammer, okay? You hit it, then you record the response on accelerometer, okay? And the response will be your transfer function, okay? For example, here, this is the transfer function, y over x. If x is the input, okay, this is the input, and it's 1. Why it's 1? Because it's an impulse. So if you calculate the output, multiply by the input, which is equal to 1, it will give you the output, okay? And we call this in control, we call it the weighing function. Just for your information, okay? What's important in this chapter is how to derive the transfer function for any given system. Okay, let's start with this basic example, how to derive the transfer function. What we have here, we have a mechanical system. Okay, we have 2 degrees of freedom. We have x, we have y. Okay, find the transfer function. He must tell you clearly what's the input and what's the output. So he told you, this is my input, x, and this is the output, y. So find the transfer function. Okay, he wants you to derive the transfer function. So how are you going to do this? You need the equation of motion. So how are you going to derive the equation of motion? You need the free body diagram, right? So I'm going to draw. And by the way, this is a problem. We don't have a mass here, but we have degree of freedom. So how are we going to handle this? For beginners only, okay? For just beginners, I will assume I have imaginary mass here, just for understanding. Okay, later I'm not going to use this procedure. So I'm going to use m naught, where m naught is equal to 0, okay? This is imaginary mass, okay? All right, and this is the displacement y, all right? Displacement y. Okay. Okay. Now, show me the reaction forces. Since y going to the right, we have a reaction force this in this way. Oh. This side, and we have a reaction force on the other side. So if you assume this in this direction is going to be how much? This one, by dot, by dot, okay, by dot. All right, and in this direction, you said against which motion? Against y. So this is going to be k times y. You said against y, right? This is against y. So you say k y minus the other displacement, which is x. Okay, and this is your free body diagram. That's it. All right. What about the free body diagram here? We're not going to do a free body diagram. There is no free body diagram here because there is no force here. If there is a force here, okay, then you need to draw the free body diagram here. Or if there is a mass here, then you need to draw the free body diagram. Okay, but since we don't have a force, it's a free end, and there is no mass, so there is no free body diagram. Okay, it's a free end. All right. So I'm going to erase this. Okay. And keep this. This is the only free body diagram we have. Now show me, they say Newton's second law, applying Newton's second law, summation of forces acting on this body times acceleration must be equal to, a summation of forces equal to mass times acceleration. What is the positive force of the positive direction? To the right. How do I know this? With y. So show me what are the forces. Minus k, y minus x minus by dot equal m x, or not x, sorry, it's y. Y dot. Okay. Now, how are you going to find the transfer function? How are you going to find the transfer function? Which is equal ys over xs. How are you going to do this? Take the Laplace transform, assuming zero initial conditions. Okay, take Laplace transform of the equation of motion, assuming zero initial conditions. So this is going to be minus k ys minus xs minus bs ys equal to m s square ys. Okay, rearrange. How are you going to rearrange this? How are you going to find the transfer function? Collect all the coefficient of y together on one side and collect all the coefficient of xs together on the other side. Okay, I wish we have more space here to make it more clear. But let's do it. It's a very simple example. Okay, so let's collect y together on one side, y together on one side, and x together on the other side. X, we have only one coefficient here, so it's going to be k xs, and y will be what? It will be k plus bs plus m s square times ys. This is s square. Okay, right? All right. So the transfer function we're looking for is what? Ys over xs. It's going to be what? The k over. Oh, we have a problem here. What's the mistake that we made? That's why I don't like to. We have a mistake here. What's the mistake? If you figure out. M naught. This is m naught. Not that we don't have a mass here. That's why I don't like to use a mass. Okay. So this is going to be 0. Sorry about this. I don't like to use mass. That's why I will try in the next example avoid using an imaginary mass to avoid this headache and this mistake. So it's going to be simply, this one will be simply what? Bs plus k. Okay, which is the same. as we got here. Okay, sorry about that. All right, in the next example, we're going to do the same thing. Okay, that's good. Same thing, but we switched the damper with the spring. We switched the damper and the spring. We're going to do the same thing, but without the imaginary mass to avoid this headache. Okay, so this is why. Show the forces acting on this dot. Okay, show the forces acting on this dot. Okay, we have force here. We have force here. So this is y, degree freedom y. What do we have for, what's the reaction force here? It's going to be K against y. And here it's going to be B, B, again, what's this? It's going to be B, S, oh, sorry. It's in the time domain. It's going to be B, X, oh, sorry again. Sorry about that. I have many things here on my table. It's confusing. I'm sorry about that. Okay. It's going to be B against what? Which one did you start with? It's against Y. Okay, so you start with Y. B Y dot minus X dot. Best. Okay, this is your free body diagram. Why we don't take a free body diagram here? Because this is a free end. There is no force, no mass, a free end. There is no equation of motion. Okay. Okay. All right. So take the equation of motion. Summation of forces equal mass times acceleration. Where is the positive direction of force? Here. Positive. So this is going to be minus B y dot minus x dot minus k y equal m y double dot. Good. Oops, we don't have m. So why we are using m? There is no mass here. Sorry. Should be 0. It looks like we are repeating the same mistake again and again. Sorry about that. Okay, so there is no mass, so it's going to be 0. There is no mass here. It's a dot. There is no mass, point. Okay, take Laplace transform, assuming 0 initial condition. Always we're going to do this step in order to find the transfer function. So this is going to be minus bs ys minus xs minus kys, it's capital letter y, equal to 0. Collect all the coefficient of y together on one side and x on the other side. So this is going to be what, ya shabab? It's going to be how much? It's going to be bs xs, and on the other side k or bs minus k times ys. So the transfer function we're looking for, which is what? ys over xs, it will be how much? It's going to be bs over bs plus or yes, this is plus. Why? Because we have minus here to the other side. Yes, plus k. Okay, so this is going to be bs over bs plus k. Is there any similarity, or can you compare this transfer function to the other one? Are they the same? No, they are not the same. Look, the denominator here is different than this one, and it makes sense because we changed the system. We switched the damper and the stiffness or the spring. But what's the similarity between these two systems? Look at the denominator. What's the power here, or the order? 1, right? So this is first order system. Here also first order system. Okay, this is first order system. First order system, okay? First order system, they always have a similar behavior. Okay, keep this in your mind. We'll talk about the behavior or the analysis of the system response in chapter 8, inshallah. Okay, so this is a simple example, this one, and the what we're going to do next, inshallah, in the next video, we will solve. This is a more, I like this problem because this is more real to the problems that you see in the homework and the exam. Okay, so we're going to solve this, inshallah, together next class. Okay, so I'm going to stop here. See you, inshallah, next video.